Hello everyone, my name is Jennifer Cain and I'm a PhD parasitologist at Parasight System. In this presentation, I'm going to discuss how we validate the Parasight System's ability to detect different parasite eggs. First, we will go over a little background, namely why on earth do we care about doing fecal egg counts in the first place. Fecal egg counts allow us to determine whether mature adult parasites are present within an animal and thus choose appropriate treatment measures. This is important because some parasites can be zoonotic and infect humans, and it is an important part of an annual wellness exam. It allows a veterinarian to help design a parasite control program, choose drugs, and assess treatment efficacy with a fecal egg count reduction test. Assessing treatment efficacy is particularly important due to the ever-increasing prevalence of anthelmintic resistance. While the issue is common in the livestock world, particularly horses, cattle, and small ruminants, it is also becoming an issue in companion animals with the rise of anthelmintic resistance in canine hookworms. There are a few factors that go into determining what makes a good fecal egg count test. Sensitivity and specificity are the ability of a test to correctly determine true positives and true negatives. Sensitivity is often thought of as how low can it go or how good is a test at detecting a true positive when egg counts are low, thus missing fewer positive cases. Specificity, on the other hand, is how good a test is at detecting a true negative, thus giving fewer false positives. These two factors are particularly important when it comes to companion animals due to the risk of zoonosis. Precision and accuracy, on the other hand, are how well a test is at getting the same answer every time and how good a test is at getting the true answer. Precision in fecal egg counts is highly affected by natural variation between subsamples due to uneven distribution of eggs and uneven shedding of parasite eggs and feces. As much as 95% of variation between counts is due to this subsample variation. Accuracy is not possible to know in naturally infected animals as there is no way to know the true number of eggs in any given sample. However, the more total eggs are counted, the closer to this true value the result is likely to be. The final important thing to note here is multiplication factor, which is often mistaken for test sensitivity. The multiplication factor is a number that is based upon how much feces is being processed, how much flotation media is being used, and the total volume of sample examined under the microscope. It is a purely theoretical value assuming perfect homogenization and egg recovery and does not reflect the overall sensitivity of a test. There are many different fecal egg count methods with tons of variations, and everyone has their favorite. Mini-Flotac and McMaster are methods where sample is placed into a slide and the eggs float in the flotation media. Wisconsin is a double centrifugation flotation method, and then there are standard centrifugal flotations, passive flotation, which doesn't require any centrifugation, and a fecal smear, which is not generally a recommended method in most cases. All of these methods have their pros and cons and all require a well-trained technician to identify parasite eggs, as well as a good amount of time with a minimum of 10 minutes to allow for eggs to float. Automated fecal egg count systems have been introduced recently to help decrease the amount of time it takes and dependence on well-trained analysts. These include Telenostic, VetScan Imagist, Kubrick Flotac, and the Parasight system, which uses fluorescence rather than gross morphology to identify eggs. In order to validate the Parasight system, we compare the results from the unit to commonly used methods. For pasture animals, this can include McMaster, Wisconsin, and Mini-Flotac, and for companion animal, it can include Ovaassay, Mini-Flotac, and McMaster counts. We assess different test parameters by performing repeated counts on the same sample. Performing repeated counts and taking the mean helps take into account some of the subsampling variability discussed earlier. We also look at different types of precision, biological and technical. Technical precision performs repeated counts on the same fecal slurry, thus removing the subsampling variable, whereas biological precision performs repeated counts on different slurries, taking into account all of the previously described subsampling variability. We have also looked at variability between analysts with and without training, as well as under time pressure, and are also currently in the process of conducting a study to assess egg recovery for different sample preparation methods. Well, in the past, for validation of the pasture animal unit, where high correlation coefficients greater than 0.7 were found between equine samples for Parasite and McMaster and Wisconsin, as well as camelid, sheep, and goats and cattle samples for Parasite and McMaster. In addition, we have also developed a genera-specific test for Haemonchus contortus, or the barber pole worm, a highly pathogenic nematode affecting small ruminants globally. This parasite has a rapid life cycle, and this combined with pathogenicity led to a heavy treatment regimen and thus the rapid development of resistance. Due to this, careful treatment programs are now in place in Australia and New Zealand to only use certain drugs when Haemonchus prevalence is high and different drugs when it is low. Previously, the only method to determine percentage of Haemonchus was via copper culture, where eggs are hatched and larvae identified in a process that takes 2 weeks and a lot of skill. A peanut agglutinin lectin has been shown to specifically stain Haemonchus, and thus we can use this system to perform counts in just 20 minutes. We compared manual and parasite counts, presented as percent Haemonchus, as well as copper culture and parasite percent Haemonchus results to show a strong correlation between all results, thus confirming the utility of the test. Presently, we are in the process of validating the cat and dog system with strong correlations for all 3 egg types. The hookworm dataset is complete, but there are still more samples needed to complete the roundworm and whipworm datasets to reach the goal of a minimum of 50 positive samples for each egg type. Triplicate counts have been performed on each sample for each method, including OVA-assay, McMaster, mini-FlowTAC, and Parasight. Presently, that is a total of over 1,000 counts. After this dataset is complete, we will perform a precision analysis where 10 repeated counts for each method using the same slurry will be performed, and the cat and dog parasites will be utilized in the egg recovery study to determine accuracy and recovery at 100 eggs per gram and sensitivity using only 10 eggs per gram. Both of these will be conducted in a perfect world with no feces in the sample and also with feces in the sample. The egg recovery portion will also include a simulation of the VetScan Images dabber to provide a comparison to this method as well. One important thing to know about all of these methods is a difference in count magnitude. Count magnitude is a reflection of sample preparation and how good a method is at recovering eggs. The more eggs recovered, the more accurate and the more likely a given method is to detect positive samples at low counts, thus making it more sensitive. The flotation methods that utilize a cover slip, both centrifugal and passive, tend to produce overall lower counts compared to other methods. This can be seen in the first graph, where the parasite samples tend to produce higher counts compared to the Wisconsin method. The same is true for cat and dog samples, expressed as total eggs rather than eggs per gram, where the OVA assay produces lower egg numbers than mini-FlowTAC and Parasite, and this is before any multiplication factors come into play to account for subsampling of the slurry. The major competing product is the VetScan Images, which has 2 papers published validating their AI algorithm. In both papers, they compared to passive and centrifugal flotation to determine sensitivity and specificity, and compared counts done on the same slide by a parasitologist to the results given by their algorithm in order to verify it. In both papers, there are less than 50 samples per egg type, and none of those had a count magnitude of over 50 eggs per gram. This means that the system is not validated for any samples with a high egg count. For example, one of our samples had 25,000 eggs per gram Toxicara eggs on a mini-FlowTAC. This can cause an issue with the algorithm and its ability to detect touching eggs. In addition, we did a simulated comparison of egg recovery using a 3D printed model of the dabber that they show for moving sample onto a cover slip in the demo videos. We did it 2 ways. The way it was shown in the video tutorial, vigorously inserting the dabber multiple times in the tube and then gently tapping the dabber on the top of the sample 3 different times. The rest of the sample was then placed into the parasite system. As you can see, the Images dabber produced significantly lower counts than the parasite system, which begs the question of what would sensitivity and specificity for this system look like with truly low counts.